Okay, so now we need to talk about capillary exchange. So let's look at a capillary. So here's my capillary. And remember that a capillary, its wall or endothelium is one cell layer thick. Okay, and we have our little heart here, and the blood runs in one end, which is the arterial end, and then it leaves the venual end to go back to the heart. All right, keep in mind the things that are in blood. So we've got red blood cells floating around, which are probably a lot bigger than I'm drawing them since this is a capillary, but I don't want to use all the space. All right, there are proteins, albumin and other plasma proteins. There may be, maybe a few white blood cells in there, whatever. There's going to be that's a good. It's going to be oxygen in there. Probably going to be some glucose in there, right? So so as the blood comes through, we want to get the nutrients out of it to go to the tissues. So if we have our little tissues here, these are tissue cells. Little nucleus there, I'll throw in there. Okay. And there's going to be a couple of different things that are happening here for perfusion, for nutrient exchange. First of all, as the blood goes into the capillary bed, the pressure, which we call hydrostatic pressure, which is just blood pressure at the capillary, and that pressure is equal to 32 millimeters of mercury. Okay, when it leaves the capillary bed, that pressure reduces to, I think, 17 millimeters per mercury as it comes back out the other end. So the pressure, as normal, is decreasing as it's moving. So that hydrostatic pressure is the pressure going this way. And it is strong, and it gets progressively weaker. Okay, so that's hydrostatic pressure. There's also another pressure going on here, and this is the pressure created by the plasma proteins. And this is going to be osmotic pressure, and this is pressure that pulls water back into the vessel. So this is osmotic pressure. So osmotic pressure is maybe 30 millimeters of mercury, or maybe it's a little less than that, I'm not sure. Anyway, it doesn't really matter. Is the osmotic pressure decreasing as the blood is moving towards the venous end? No. Osmotic pressure stays the same throughout the entire capillary bed because it is created by plasma proteins, not by the fluid inside the vessel. There's the same amount of plasma proteins here as over here. It's just all floating around. So that is what's causing that osmotic pressure, which is pulling that fluid back into the vessel. All right, so certain things are happening here, different types of movement. And the first one, let's see, is diffusion. Diffusion is what moves oxygen across. Oxygen moves out of the vessel down a pressure gradient. We call it a partial pressure gradient, which we will talk more about when we get to the respiratory chapter. But there's diffusion going on, and that's allowing oxygen to go into the cell. It is also allowing carbon dioxide to move into the vessel. So CO2 will also move the same way down a partial pressure gradient into the vessel. Okay. Another way that movement occurs is through bulk flow. So this is a function of hydrostatic pressure. It's pushing water out. It's pushing water out more at the beginning of the capillary bed and less so as it moves along and towards the end of the capillary bed. This is the filtration of water. So we're seeing filtration here. So the fluid is filtered out into the interstitial space from the capillary bed. It's pushed out through that hydrostatic pressure. And with it, some things will move. It'll be pushed out. Some stuff will go with it. Okay? The next movement is osmosis. So this comes from osmotic pressure. And it's pulling the water back into the capillary. Pulling water back into the capillary. Oops, sorry. This is called absorption. Okay, so in this scenario between diffusion, bulk flow, osmosis, and really between bulk flow and osmosis, more, put this in another color maybe. So more fluid is moved out or filtered than is absorbed or moved back in. So at the end of a 24-hour period, the net filtration left over in the interstitial space is about 3 liters. So that 3 liters of fluid would just build up and build up in the interstitial space, and you would blow up like Violet Beauregard in Willy Wonka and the Chocolate Factory. But that doesn't happen, and there's a reason why that doesn't happen. And the reason why it doesn't happen is something called the lymphatic system. So we have lymphatic vessels around the capillary bed to absorb or to pick up that excess fluid. All right, so that is basically capillary exchange.